So here's the whole setup. All is vacuum controlled, so we can put the samples in here. The vacuum will hold them on the right place, get it under the lamp, and the lamp and this is the lamp power supply, normal xenon UV lamp, and turn it on. And here's the flux controller to control how much irradiation is put on. Basically, it's we can set it up to provide the correct amount of irradiation. We can set it to apply the irradiation for the time, and even program it so it will irradiate the sample in a couple of bursts. When I open, you can see UV light. Very well controlled.
How do you apply the photoresist to the surface of the
on the surface of the sample? The spin coater out there is to use. We will finally bring it here, so we can like prepare the chemicals out there. Then we get the spin coater running here, cover the sample with the photoresist on a spin coater, and apply the mask on the photolithography setup.
And then to remove the photoresist.
And then to remove the photoresist, we can do it here. If it's so low, so narrow trace thickness, or do it outside with the chemicals.
So here, usually to make the lithography, you need to work like a team, and someone is working in the other room.
No, basically, in the process of photolithography, we cannot work alone because we use chemicals. There's use of chemicals. The room is called clean room, but it's not very well ventilated, so the gas can accumulate in here. And when someone faints, there's actually a monitoring system as well, so someone outside will sit and watch what happens with us, and to be on a safe side.
So could you explain me the color of the light that you are using?
The lights are there can be white light, normal visible light, normal white light turned on, but for the photolithography process we use red or yellow light. It depends on the photoresist that we use. Most of them are sensitive for the UV light, so if they are sensitive for the UV light, they will be not sensitive for the light on the other end of the spectrum, so red and yellow as well.
Okay.
So when we apply the photoresist on our sample, in this light it won't be exposed. It won't. We won't damage the resistant layer. Just enter this room.
Okay, and the lithography process you are using to produce solar cell in what way?
We are currently not not using photolithography. We think that the best way to use a photolithography would be to control the surface, like the surface structure. So when you etch silicon, it is basically etched in this manner that you apply the photoresist. The MEMS, for example, MEMS things are made this way, or AFM probes as well. You apply the photoresist, and there's this tiny hole in it after the photolithography, and when you etch the silicon with the phosphoric acid, it will etch down this way with the correct angle. So when we apply the photoresist in, like, for example, in the way of vertical or horizontal stripes, we can then etch the layer to form zigzag. So the surface area of the sample will be actually bigger than the sample surface area in nanoscopic level, per centimeters.
And why do you want this surface on the solar cell?
We want the surface of the solar cell be as big as possible because the whole energy production is achieved only on the surface. So stacking, for example, stacking two solar cells, the first one will produce their energy, and the second one, maybe if the first one was thin enough to actually provide some light on the second one will produce, but the third or the fourth won't produce. But when we do it like this, the one cell will have a lot bigger surface area, for example, twice the surface area, then it will be able to produce more energy. From in microscopic, the two cells are the same. The one is 1 square centimeter and the other is square centimeter. But the flat one has only this 1 square centimeter, and this etched one will have 2 square centimeters to produce the energy. So, considering that the flat one is like 90 degrees, so more energy, so we will have 150% or 160% of increase in power.
Okay. And with this lithography process, could you create you make the contact, the fingers of the cell?
Yes, as well. It's the same thing that. But instead of like etching the silicon, we just put the mask of the fingers of the contacts, do the photolithography, and for example, spider, I don't know, copper, and on the copper just to protect it, we will spatter some tin materials.
Okay. And what is the thickness of the sample that you are working to create these solar cells?
Actually, now we are trying to in one micrometer, so 700 nanometers of absorber layer and around 300 nanometers of window layer. So the whole sample will be the silicon will be only like 1 micrometer.
Why do you say silicon? Because I suppose that this is very thin and could be, very thin. But how do you provide some
support?
Yes.
We are planning to use. We are now using glass, but it may be used on like aluminum or other metals or even ceramics.
If you put glass, I think that you are going to have a problem with the contact, with the contact that you need to have.
Yeah, the bottom contact that won't be irritated by the sun is all usually like copper. But the top one, we are using TCOs, transparent conductive oxide. So we are working on producing ourselves the indium tin oxide and tin oxide for in a process called reactive sparring. So we get tin and indium or indium tin alloy, and we spar it on the line setup with the use of oxygen.